Let's wait for a couple of minutes and get started. I think people are still joining. Hope you can hear me and see my screen. Great. Thank you. Okay, let's get started. So, welcome to the week 5 live session for the GPU Architectures and Programming course. Hope the course is going along well for all of you. And for anyone who's joining this for the first time, it is a 2-hour session. Interaction will be through the chat box, and post the session, you will get access to the slides and the recording. And we'll have a 5-minute break around 8 o'clock so that you don't get too overwhelmed. Yeah, so I'll be addressing all of week 5's content. We'll start with a quick recap and then we'll take 1 hour for problem solving. And I've moved the previous week's questions to the end of the session. So I think there were a couple of questions last week on kernel launch and something else. So we'll get to that towards the end of the session. So please keep it interactive. Whenever we discuss problems, I will give you time to solve them. So please take that time, solve them, and post your answers on chat. It doesn't matter if it's right or wrong. It'll just give me an idea as to what you find confusing and whether something is very clear, and that way I can structure my explanations accordingly. With that, we'll move to today's content. So mainly week 5's portions were around warp scheduling and divergence. So till week 4 we had looked at grids, threads, blocks, and we had seen kind of various calculations on what happens if you change this parameter in a kernel launch. This week we looked at how that maps onto hardware. So we took a few examples, and we will be seeing more examples through today's session also. If you take a kernel with a certain launch configuration, how does it map to hardware? And sometimes you have to remember that while we theoretically discuss something, in practice it might not actually happen that way, because when we are doing certain examples, we assume that memory is not a constraint, but memory might be a constraint and you might not see the behavior you're expecting to see. So just keep that in mind. I'll again touch upon it when we come to the problems. So we looked at the GPU hardware scheduler very briefly, and we spoke about the concept of a warp and how it is scheduled. And we also looked at control flow divergence, right, which is the main topic of week 5. So we took a simple branching example and spoke about divergence, and then we also took a nested branching example and saw how divergence is handled. So this is broadly what was covered in week 5. So we'll start with a quick recap of some of these topics, not all. And if you have doubts on any one of them and you don't understand it very well, feel free to post on the chat box. I'll either take it up today itself at the end of the session, or put in additional content in the next week so that you can kind of clarify that particular concept. But let's get started. So again, as a recap, so all of you are already familiar with the terms SM, SP, block and thread, right? So what are some things to keep in mind for the GPU scheduling? First of all, one block goes to one SM. You cannot have one block spanning multiple SMs. Some of these things are kind of hardware constraints because of the way the hardware and the architecture are designed. So you have to keep it in mind whenever you design kernels or whenever you solve problems. The second thing is one SM can have multiple blocks, right? So these are kind of the 2 points on blocks and SMs that you should remember. And here is an example. If an SM can have a maximum of 1024 threads or thread contexts and the block size is 256, we have 4 blocks per SM, right? This is just simple math. So we'll skip through this. We'll see more detailed examples through the problems today. So coming to a quick overview on the hardware scheduler. The hardware scheduler decides which threads to map to a collection of SPs, right? And we already spoke about this. These threads are going to execute in parallel, except of course when there is some divergence. But other than that, they all will be executing the same instruction. So this unit of threads, which is typically 32, is called warp, right? And this also gives rise to the SIMT model of execution. Next, so this was an example that was discussed. So first of all, these are your system constraints. You can have a maximum of 8 blocks per SM and a maximum of 1024 threads per SM and a maximum of 512 threads per block. So these are the system constraints given to you. Now here are a few configurations of the block size and then the consequences of what happens with that block size. So let's say our input block size is 8 cross 8, right? And threads per block basically becomes 64, right? 8 into 8. And now blocks per SM, let's say that is 12. So then what happens? You can have, so the SM resources will be underutilized. Why would that be? You have 1024, a maximum of 1024 threads per SM, but here you are utilizing less than that, right? Because you're doing 64 into 12. That's basically how many threads you will have. So that comes out to be something around 700, 800, right? So you will not be using the maximum 1024 threads. So your execution resources will be underutilized. Then in the second case, we have 16 cross 16 as the input block size, which means that your threads per block is 256. Now in this case, you have 4 blocks per SM, and that itself gives you the maximum, right? And so you achieve this 512, you achieve the maximum thread capacity in your SM, and therefore there is no underutilization that we saw in the previous. You achieve the maximum capacity of 1024, not 512, sorry. So you achieve your full thread capacity. Now in the third configuration, you have 32 cross 32, which comes out to be 1024 threads per block, and just 1 block per SM. But this exceeds the threads per block limit. So see how these kind of different limits come into play, right? The blocks per SM, the threads per block, threads per SM, all of these. So all of these are whenever you take a kernel and launch it with some parameters, the scheduling that actually happens considers all of these parameters. So that's something you should also try to keep in mind when you solve questions. Okay, coming to control flow divergence. So typically we said threads inside a warp execute the same instruction. But what if there is an if statement or a branch instruction, which means that certain number of threads should execute one thing while other threads will execute something else. So this is called divergence, right? This is called control flow divergence. And what happens then is you cannot run both of these at the same time. So a certain number of threads will pause, and a certain number of other threads which fulfill a condition. For instance, if it is if something, execute this. Let's say that those threads which fulfill that if condition will execute the block, while the others will be halted, and then the other set of threads will execute. So this is how control flow divergence is handled. And we have an example here. Let me just get a pen. Yeah, so here your condition for divergence is thread ID mod 2 equal to 0. So basically all your even threads will execute something, all your odd threads would execute something. And you have this notion of a mask, right? How does the hardware do this? There is a mask and the mask bits are set to something based on this condition. And then after this block executes, the mask bits are complemented so that the other branch, the other threads corresponding to the other branch execute, right? And that's how divergence is handled. And then after this part of divergence, it converges again. The flow converges here. So this is a simple example. So with this, we will go directly to the questions. Before that, I will wait 30 seconds to see if you have any questions on any week 5 content. If so, I will, like I said, I'll either address it towards the end of the lecture or in the next live session. But please post a question saying this part that was covered wasn't clear, so that I know what you're looking for. Okay, latency tolerance. Let me see if I have slides on that. I don't think so. If not, I will take that as an input and then cover it in the next week. Yeah, I don't think I have slides, and it's always good to explain with an example rather than talk about it very abstractly. So, yeah, let me do that in the next class. Any other concept? Okay, if not, let's move on to the discussion forum questions. So these are just questions that were asked in the discussion forum, and I've put them here in case you haven't seen them. So we'll just quickly go over them and what answers the official TAs have given to them, right? So there was one question from the week 5 assignment with question 1. So let's go through this. So the person asking the question says data given in the question, grid dimension is 4 2, block dimension is 8 4, number of SMs is 4, SPs per SM is 32. How many thread blocks of the kernel are mapped to single SM? So this is the way the person has worked it out. Grid dimension is 4 2, total number of blocks launched is 4 into 2 8. Now an entire block must be mapped to one SM, number of SMs equal to 4. So each SM will have 2 blocks assigned, and therefore the answer should be B, that is 2. And block each block has dimension 8 into 4, which is 32, and these 32 threads can be mapped on the 32 SPs that are available in each SM. But the answer given is not 2. I think the answer given was 1. So the person is asking how is the answer 1, right? So the only difference here is when the question says how many thread blocks of a kernel are mapped to a single SM, the implicit part is how many at a time, right? Whereas I think this person was confused because they calculated it for the entire kernel, and this question might have been more clearly worded. For instance, how many thread blocks of a kernel at a time are mapped to a single SM, but unless it is otherwise mentioned, you can take it to be at a time, right? In case they want you to answer the total number, they'll always mention it as in total, or for this kernel how many batches of something like that. You will see wording that implies they are asking you for the entire kernel, right? So that's the main reason for the confusion in this question. Now let's go through the solution given by the TAs. So again, it's the same thing. Each SM has 32 SPs and the block dimension is 8 4, which equals 32 threads. Now each SM is given one thread block with 32 threads, so that you utilize the full potential of all of these SPs. And there is a following question that is asked, and that question touches upon how many batches of blocks are deployed on the hardware. So in this question they are just asking you about at a time how many blocks are mapped to a single SM, and therefore the answer is not 2. Hope this is clear. Any more questions on this? And if you see such questions where you see ambiguous wording, right, feel free to ask it while the assignment is live. Whenever you read a question, first try to understand if there are multiple ways of interpreting that question, so that you don't kind of understand it in a way that was different from what the TAs or the course instructor meant it to be. So you can ask on the discussion forum if you have a kind of a confusion as to what the question means. Okay, if not, let's move to the next one. So this is more of not a numerical question, just a conceptual one. Can you explain how do the concepts of blocks and grids actually map to the architectures with TPCs, SMs, SPs discussed? So this is kind of a very nice question, right? So you learn a lot of things at the software level. As a CUDA programmer, how do you write a kernel with these grids and threads and blocks? And you also learn at a hardware level from the architecture perspective a GPU looks like this. It has so many SMs, it has so many SPs per SM. But the key part that often is tough to understand in a course like this is the link between the two. Um, let's say I write a program like this. How does it actually get mapped to the architecture below, right? So that's what is being asked in the question. So let's read through this answer and try to make sense of it. In CUDA, blocks and grids are used to organize and schedule parallel computations on the GPU. Each block represents a group of threads that can be executed in parallel, while a grid is a collection of blocks. This part I think all of us are kind of familiar with. So we express computation in terms of grids, blocks, and threads. So it's this hierarchical notation, right? And I think in one of the earlier classes I gave you this example of a word on a page and using something like a paragraph number, a line number, and then a word number, right? You can think of the hierarchical notation in that way for simplicity. Next, they say the mapping of blocks and grids to the GPU architecture depends on the specific GPU being used as well as the configuration of that GPU. Generally speaking, a CUDA enabled GPU consists of several streaming multiprocessors, each of which contains multiple processing cores called streaming processors. Again, this point highlights one thing, that there is a hardware dependence. Hello, am I audible? Okay, I think I had a temporary network glitch. Hope I am still audible. If not, please post a message on chat. Let me continue. So, this point tries to tell us that this is not a hardware agnostic thing, right? It depends on the GPU heavily. The way we decide this number of blocks, number of threads, all of this has to take into account the GPU architecture and the configuration of the GPU. For instance, how many SMs does it have? How many SPs does it have? How many blocks are allowed per SM? How many threads are allowed per SM? All of these are important constraints to keep in mind, and those are architecture dependent. Then the third point says, when a CUDA kernel is launched, the blocks are distributed across the available SMs in the GPU. Each SM schedules the execution of the threads within its assigned blocks, and each thread is executed on one of the available SPs within that SM. So just the way you have blocks and threads, you have SMs and SPs, right? So first you distribute the blocks among the SMs, and then within an SM you distribute the threads across the SPs. This is how it happens. So intuitively, what every kernel you write tries to do is to have as much parallelism among the blocks. Basically, you want all the SMs to be fully utilized. Further, in every SM, you want to spin up as many threads as possible, because within that SM also you want its full capacity to be utilized so that your program gets the highest benefits. So this is the how you map the blocks and threads onto the SMs and SPs. Now the last point talks about how do you choose this. The number of blocks and threads in a CUDA kernel can be chosen based on the specific problem being solved and the capabilities of the GPU being used. The optimal configuration will depend on factors such as the amount of parallelism in the problem, the memory requirements of the kernel, and the number of available processing units on the GPU. Right, so this again tells you that it also depends on the problem being solved. Let's say, so for instance, we saw this notion of a 2D array and a 2D grid and block, and we also saw that, so we had some slide in the week 4 content saying if you have 2D data, you should be using 2D blocks and grids, and if you have 3D data, you should use 3D launch parameters and things like that, right? So it depends on the problem being solved, and every kernel you launch, the memory requirements of that kernel also play a role. So let's say you want to spin up 32 threads in a particular block, and this block goes to 1 SM. But the memory required for this 32 threads may not be available on that SM, and therefore, and this memory is problem dependent again, right? If I do addition, that would be different from doing multiplication. So this memory requirement is problem dependent. So this point highlights that it's a combination of the problem and the architecture of that particular GPU. So you can't arbitrarily say, if I give you a problem and say what is the best block and thread for this problem, you can't really say that because you don't know what hardware it will run on. And if I give you a hardware and ask you what block and thread should be used for this hardware, you still can't say that because it depends on the problem being solved. Some configuration might work very well for one problem and might not work well for the other problem. So it is kind of a mix of the two, and that's why it involves some amount of trial and error also most of the times. Okay, is this clear, or are there any questions about this? Okay, if there are no questions, we can move forward. Okay, so with this, we are done with the recap and the discussion forum. I think there were 2 questions from the previous week, which I will do after the problem solving session. So let's get started with this. So here's the first question. Consider the following grid and block dimensions for a kernel. Grid dimension is 4, 2, block dimension is 4, 4. For a hypothetical GPU architecture where number of SMs is 4 and number of SPs per SM is 32, how many thread blocks of the kernel are mapped to a single SM? So this was very similar to what we just discussed, but go ahead and try and solve it. I'll give you 2 minutes for this. And when you have an answer, please post it on chat. Any answer so far? Is the question clear? Or do you feel the question is okay? Option B, 8 thread blocks. Anyone else? Any other answers? If not, let's take a look at the answer and see what it is. So it is B, 2 thread blocks. So let's see why that is, right? So first of all, how many blocks do we have? We have 4 into 2, 8. And each of those blocks has 16 threads. And now we have 4 SMs available to us. So how can we split up these 8 blocks across them? We can take 2 blocks per SM, right? And does the SPs kind of align nicely with that? So each block has 16 threads, and the target architecture has 32 SPs per SM. So if you schedule 2 blocks per SM, then the number of threads for that 2 blocks would be 16 into 2, 32. And you can have those 32 threads be split across the 32 SMs. So this is this gives us the answer, that is 2. So I think one of the other answers was 8 thread blocks per SM. So let's think about that. What would happen if we did that? So we have a total of 8 blocks, and we are putting all of them onto a single SM. And that would mean the total number of threads that you have is 8 into 16, right, which is 128, but you only have 32 SPs. So a first set of 32 will get scheduled, and then the next set, and then the next set, and so on. So this is kind of a suboptimal way of scheduling. So the intuition or the idea when you see such a question is, first think of the total number of blocks, which is 8 here, and the number of SMs, which is 4. If you had only one SM, you don't have much of an option, right? You would have to go ahead and schedule all the 8 blocks on the 1 SM. But now that you've given 4 SMs, will the scheduler go ahead and schedule all the blocks on that one SM while the other 3 are idle? If it does that, it loses the benefits of having those extra 3 SMs, because you're forcing everything to be scheduled onto 1 SM. So it's kind of like distributing the number of blocks across the SMs. So your total number of blocks is 8, and the number of SMs is 4. So if you had to distribute these 8 blocks across your 4 SMs, you would give 2 thread blocks to each SM, assuming that this SP calculation worked out fine, right? So that's how the answer comes out to be 2. Is this clear, or is someone still wondering why it is not 8 or why it's not 4? Okay, I'm guessing that's clear. Okay, then let's move to the next question. Okay, So this uses the data from question 1. So I can scroll back after reading this. After deriving the number of thread blocks that can be scheduled to a single SM, how many batches of thread blocks to SM dispatch would be required to complete the kernel? So we already spoke about how many thread blocks would be scheduled to a single SM. We said 2 thread blocks would be scheduled to a single SM. Now this question asks us how many such batches of thread blocks would need to be dispatched to complete the kernel. So think about this. Your options are 1, 2, 4 and 8. I'll scroll back here so that you have the data. Any answers so far? Okay, answer is 2. Okay, let's look at that. Any other answers in the meantime? Okay, no one else has an answer. Let's take a look at the solution. So the answer is 1. So let's go through why that's 1, right? So we said we have 4 SMs and we would dispatch 2 thread blocks to the SM, to each SM at a time, right? So you have a total of 8 blocks and you're dispatching 2 thread blocks per SM, which means across the 4 SMs you dispatch all 8 blocks. And you have a total of 16 threads here, and you have, since you have 2 blocks per SM, you have a total of 32 threads, and since you have 32 SPs, all of them can be executed. So would you need another batch of dispatch? That's the question. So if you one way to calculate this is to look at the total number of threads that is needed for this problem, right? So you get that by multiplying 4 into 2, 8 into 16, which comes out to be 128, right? This is the second part. This is the total number of threads to be launched for that kernel. How many are we launching now? So in each SM we are having 2 blocks, which is 2 blocks of 16 threads each. So per SM we have 32 threads, and across 4 SMs we have 128 threads. So you finished, all of this is in one batch itself. So you finish everything in one batch. Therefore, one batch is enough and your answer is 1, right? So, let's see if we can find a simpler framing to this question if you're confused, right? So, going back to this question, another way of thinking about it is, let's say we have 4 rooms, right? And let's say this is some movie or whatever going on, right? And you are kind of the scheduler, you decide which people go to which rooms. Now let's say each of these rooms can occupy 32 people, right? And you have a total of 128 people waiting. Now if I put in 32 each across the 4 rooms, how many batches would I need to schedule? Let's say this is one run of the movie, right? If I'm able to finish off all 128 people who are waiting in this one run, then do I need to have another batch of scheduling where, say, I let in some people to watch a later version of the movie? I don't, right? Because I'm finishing off all the people. So that's how it is. And this question was talking about how many seats you have in that individual room. Now it's possible that I can schedule 64 people also to this room, but this room has only 32 seats. So what happens if I schedule 64 people? They will have to wait for the first 32 to finish and go out, and only then can the next 32 people go out, while the other room is actually sitting empty because there's no one there. So I wouldn't do that. What I would do is split this 64 into 32 and 32. So that was this question. Now the second question was asking us, how many times do I need to do this with this configuration? Hope this analogy helps you understand this better. I know there are a lot of such questions and it might seem very confusing initially. Does this help? Is it clearer? Any doubts on this? If it's still not clear, feel free to ask. I'll try to come up with a better explanation maybe by next class. But if you don't understand, feel free to say that. Okay, I'm assuming there are no questions. Let's move forward. Okay, so now again using the same data as question 1, but a different GPU architecture. Now this different hypothetical GPU architecture supports 2 SMs and 16 SPs per SM. Now with the same kernel launch parameters, how many thread blocks would get mapped to the same SM? So now let's just write down the launch parameters. So it was 4 2 and 4 4, so that you can solve this easily. Again, I'll give you 2 to 3 minutes. Think about it and let me know when you have an answer. Okay, 8 blocks per SM. Anyone else? Any other answers? Okay, let's take a look at the answer. So the answer is 1. So let's again think about this. So our launch parameters were 4, 2, which is again 8 blocks, a total of 8 blocks, and each block has 16 threads. In the previous case, I had 32 SPs per SM, so I could schedule 2 blocks per SM because I had those extra SPs and I could run 32 threads. Now there is no point in scheduling 2 blocks per SM because that would lead to 32 threads, but I only have 16 SPs. So all I'll do is schedule one thread block at a time to the same SM, right? Again, the implicit part here is at a time, not across the kernel. If you look on total for the kernel, then the answer changes. I think that would be your next question, so I won't go into that already. So coming to one of the answers given as 8, let's think about what happens if the scheduler went and scheduled all 8 onto one SM. Again, I'll use the same analogy. You have 2 rooms or 2 SMs, right? And you have 8 blocks. Think of this as a bunch of people. Now, if I sent all the people to this room while this room was empty, then that is not utilizing my resources efficiently. So the GPU scheduler will not try to do this. It will try to distribute the load equally among all the SMs. So here we have 8 blocks. So it will schedule one block here and one block here, and then the next here and the next here and the next here and so on, right? And why is it one block per SM and not more than that? It is because of the SP limitation. Since we have only 16 SPs and each block has 16 threads, we will not be able to gain any more benefits by using more than one block per SM. Therefore, the answer is 1. Is this clear, or is it still very confusing? I'll just pause here for 10-15 seconds. If you're still confused, try to go through it again and see if it makes sense. Okay, you understand. That's good. So whenever you get such problems, think of it from those two intuitive principles I gave you, right? What does the scheduler want to do? It wants to utilize all the SMs well, and it wants to utilize all the SPs well. So if I gave you a certain number of blocks and a certain number of SMs, you would try to distribute those blocks fairly among the SMs. You wouldn't want to put all of them to one SM, because then the others are going to sit idle, right? You can also think of it as if you were managing a team and you had some amount of work and some number of people, you wouldn't want to typically give all the work to one person and let the others stay idle, because that's not utilizing your team very well, right? So that's the idea behind this question. So let's go to the next question. For the new GPU architecture in question 3 and the same kernel launch parameters from question 1 and 2, how many batches of thread block to SM dispatch would be required to complete the kernel? So this is very similar to question 2, just with a different number of SMs and SPs. And the launch parameters are 4.2 and 4.4. Think about this and let me know the answer. Okay, 2 batches. Anyone else? Anyone else who agrees with 2? Anyone who has a different answer? Don't worry if you're wrong or right. We're all here to learn, right? It's okay. If not, let's go look at the answer. So the answer is 4 batches of dispatch. Okay, so we can solve this 2 ways. So let's talk about both the ways. So here we discussed that there are 2 SMs. So let's actually draw this out. I think that gives us some clarity rather than just looking at the numbers, right? So you have 2 SMs and you have 8 blocks. Where does this 8 blocks come from? It is from this launch parameter, 4 into 2, that gives you 8. So the total number of blocks that you need for this kernel is 8 blocks. Now we have said as part of this question that we are going to schedule 1 block to SM1 and 1 block to SM2 in the first round. This is all. We cannot do any more because we have a limitation of number of SPs. So the second time, so only 2 blocks are over out of the 8 now. So the second time we'll schedule the next 2, and the next time we'll schedule the next 2, and then we'll schedule the next 2. So this question is asking us how many batches are needed. So it's 1, 2, 3 and 4, right? That's why the answer is 4. Here's another way of doing it. This is using the threads. The way I explained to you was using the blocks. Now, here what we do, we look at the total number of threads that are needed for this kernel. How many threads do you need? 4 into 2, 8. 4 into 4, 16. 16 into 8 will give you the total number of threads for this kernel, which is 128. And this is one part of it that you calculate. At a time, how many threads are you launching? So we are launching 16 threads per block and we have 1 block per SM. So we launch 16 threads here, 16 threads here. So at a time we are launching 32 threads, but we need a total of 128, right? So 32 into x equal to 128, x equal to 128 by 32, which also gives you 4, right? You can do this using threads, you can do this using blocks. Ultimately the answer is 4. It's how many times do you need to dispatch to the SM. Is this clear now? Okay, any doubts? Okay, if not, I think we're almost at 8 o'clock. So let's take a 5-minute break. I'll stay on the call, but I'll continue at 8:05. So see you then. Use the break to kind of refresh and come back. Okay, let's continue. Which of the following statements is true? A CUDA thread block can execute in multiple SMs of an NVIDIA GPU. Multiple thread blocks can execute in the same SM of an NVIDIA GPU. Threads belonging to different CUDA thread blocks can communicate using shared memory. Threads across multiple CUDA thread blocks can be synchronized using sync threads. Which do you think is true? Any answers? Okay. A CUDA thread block can execute in multiple SMs of an NVIDIA GPU. Anyone else? Okay, let's look at the answer. It is B. Multiple thread blocks can execute in the same SM of an NVIDIA GPU. So, I think we already discussed at the very beginning that this is a constraint. One block can only be in one SM. You can't take a block and split it into two SMs, right? For instance, you can't, going back to our analogy, let's say you're putting people to rooms, right? You can't split one person across two rooms. You can put 10 people in one room. You can't put one person in both room 1 and room 2. It's the same analogy. So, coming back here, that's why this question, this is false. A block can execute in multiple SMs. It cannot, it can only execute in one SM. But you can have multiple thread blocks in the same SM. That is possible. And these two, okay, I meant to put in explanations here because people might have forgotten, but looks like I didn't finish it. So synchronization, I think you guys saw it in the week before this, where we said that we would be synchronizing not across blocks but within a block, right? Because across a block is how you get concurrency benefits from the GPU. And if you put synchronization across a block, then you don't get scalability. So synchronization with sync threads is always within a block, right? So this is also false. And similarly, if you go back to your memory, types of memory in the GPU, you will remember that this is also false. Threads belonging to different thread blocks can communicate using shared memory. So this is the only one that is true. Basically, you can have, like we saw in our examples, we saw that in this question, for instance, we saw that two blocks would go to one SM, right? So it means that multiple blocks can be mapped to a single SM. So this is 2. Any doubts on this? Is this still very confusing? Okay, if not, I think we'll keep moving because we have a good number of questions left. But stop me any point when you have doubts. Consider a GPU architecture where the warp size is 16. What are the total number of warps launched during the lifetime of a kernel with the following launch parameters: 1, 1, 1, 32, 32, 1. Think about this. I'll again give you 2 minutes. Any answers? So just to remind you, if you're confused by what a warp is a bunch of threads. Typically the warp size is 32, meaning 32 threads form a warp. Here we are told the warp size is 16, meaning 16 threads form a warp. So then how many number of warps are launched for this kernel? Now is it easier to solve? Okay, B 32. Okay. Anyone else? Okay. If there are no other answers, let's go ahead and check the answer. The answer is 64. So let's see how we get to that. So as usual, to get the total number of threads for this kernel, remember that this is the number of blocks. Multiplying these three gives you the number of blocks, and this gives you, multiplying these three gives you the number of threads per block. So the blocks and per block gets cancelled, and all you are left with is the total number of threads. If you ever get confused by how do you get the total number of threads, simple thing is to use your units and dimensions, right? This is number of blocks and this is number of threads per block. So just multiply that and you'll see that you get total number of threads when multiplying this. So here ignore all the ones. So you have 32 into 32, which is 1024. So the total number of threads launched for this kernel is 1024. Now the question is not asking the number of threads, it is asking the number of warps. Typically, if your warp size is 32, you would do 1024 divided by 32 and you would get the answer as 32. Here we are told that the warp size is 16, therefore we divide by 16. And we get the number of warps as 64, which is option C. Any doubts here? Okay, if not, let's move ahead. Consider a hypothetical GPU architecture where the warp size is 8 and a kernel program which is launched with a configuration where the total number of threads in a thread block is 32. The total number of warps launched per thread blocks is thus 4. Consider the following conditional statements in the kernel. If thread idx.x less than 16, if thread idx.x mod 2, if thread idx.x mod 32, if thread idx.x less than 8, right? So these are 4 statements given to you for this kernel. Now the question is, which of the following options is correct? All conditional branches 1 to 4 are divergent for all warps. Conditional branch 4 is not divergent for warp 0. Conditional branch 2 is divergent only for warp 0 and 4. Conditional branch 1 is divergent only for warps 0 and 1. So I think this kind of requires you to scroll between the two. So I'll scroll back here, and when you want me to move to the options, you can let me know. If you've noted this down, I'll scroll to the options and wait there. Okay, we have one answer saying A. All conditional branches 1 to 4 are divergent for all verbs. Okay. I'll wait 30 more seconds and then we'll discuss the answer. Okay, let's go ahead and take a look at the answer. It is B. Conditional branch 4 is not divergent for warp 0. So first let's write down the thread IDs corresponding to every warp, right? We are told that every warp size is 8 and the number of threads in a block is 32, right? So you have 4 warps. This is simple multiplication. Total number of threads per block is 32. Warp size is 8. Number of warps is 4. Now let's look at the thread IDs in every warp. So you have 32 threads per block and that's divided as 8, 8, 8, 8 into these 4 warps. So here are the thread IDs. Now the option 1 says all conditional branches 1 to 4 are divergent for all warps. So this is the condition. Thread IDX less than 16 and the other one is mod 2, mod 32 and less than 8. So if you actually try out less than 16, is it really divergent for your warp 0? It is not, right? Because all of them satisfy thread IDX dot x less than 8. This is your option 4. And therefore there is no thread in warp 0 that does something different. All of them fall into the if true. Whereas if you look at the other cases, right, mod 2, in every warp there are a certain number of odd threads and a certain number of even threads. So this is divergent for all warps. And this one, thread IDX dot x mod 32. So this one again would not be divergent, but I think that is not in your options. Yeah, that is not in your options anywhere here other than this. So this is false because you know one thing that is not divergent, right? You know that option 4 is not divergent for warp 0. So that itself is one option. So you can rule out this and pick this. And additionally, if you want to go ahead and evaluate C and D, conditional branch 2 is divergent only for warps 0 and 4, which is false. As we discussed, this has even and odd numbers, so it is divergent for every single warp. So this can't be true. Then conditional branch 1 is divergent only for warps 0 and 1. That is also false because it is not divergent for any of the warps, right? Less than 16, all of the threads in warp 0 and warp 1 will satisfy it. and all of the threads in warp 2 and 3 will not satisfy it. So it is not this statement that it is divergent for 0 and 1 is not true. Therefore, we come to the answer that 4 is not divergent for warp 0. Is this clear? I'll wait here for a few seconds because I know this is a long question. Any doubts on this? Okay, if not, we'll move ahead. Consider the following kernel processing A, which is an 1D array of 2048 elements on a GPU architecture where the warp size is 16. The kernel is launched with a configuration of 6411 blocks of 3211 threads. Assume that every element is initialized to 0, and this is the kernel 1. So you have the thread ID and another statement for the GID. Now after that we have a statement that says loop bound is thread IDX dot x divided by 8. If TID mod 2, you will execute this basically in a loop till it hits this loop bound value. You will increment the value of A corresponding to this GID, and this is the program, and the initialization is to 0. After the execution of the above program, what would be the value of A1035? So I'll scroll back. Your options are 0, 1, 2, 4. Note that down and note down this 1035, and we'll go back here. So we are trying to find out the value of A1035. So think, what would the value of loop bound be? How many times would this increment happen? And then come up with the answer. I'll again maybe 2 or 3 minutes for this. Anyone? Okay, let's take a look at the answer and solve this step by step. So the answer is 1. Let's see how we come to that, right? So now we are asked to find out for a of 1035, right? Now that is your GID. Now what is your thread ID corresponding to that? So remember that there are 32 threads per block. So if I ask you, and we are still going with the assumption that every thread maps to one element. So if I ask you the thread ID corresponding to 1035, it would be 1035 mod 32, because whatever is a multiple of 32, that would be one entire block. After that, whatever is left over, that would be the thread ID, right? So in this case, 1024 is a multiple of 32. So that many blocks would have been allocated to that many elements. And then your leftover element or number is 11, right? So the thread ID is going to be 11 corresponding to A1035. So this is the thread ID within a block. Now let's calculate loop bound. Loop bound is 11 by 8, and since this is an integer, it goes to 1. Now if thread ID mod 2, 11 mod 2, which is 1. So the if evaluates to true. So it will go into this branch, and for I equal to 0, I less than 1, I plus plus. So there is going to be one increment, and since the initialization is 0, this first increment will make it 1. Now loop bound will become, I will become 1, and I less than loop bound is no longer true, and it won't be incremented again. Therefore, the value of this element becomes 1. Now is this clear? Or is it still very confusing? Okay, it's clear. Good to know that. Let's move ahead then. Okay, great. Good to know that. Assume that there is a 1D input array of n integers where each element is of the form a of I equal to I from 0 to n minus 1. Consider the following kernel code snippet executing on a GPU architecture where the warp size is 8. So this is the kernel. What it does is, first you get TID as thread ID x.x. If not of A of TID mod 8, B of TID plus equal to square root of A of TID, else you add this once and then add again the square root of A of TID, and then the above code represents a kernel suffering from divergence. During the lifetime of warp 0, what are the total number of square root instructions that are executed? Options are 0, 15, 31, 9. So what is asked is very simple. For warp 0, how many square root instructions are executed? So these are your square root instructions, right? So warp size is 8, and for warp 0 we are wondering how many square root instructions are executed. So think about that. We'll take 2 minutes here again. Okay, 0. Okay, anyone else? Let's wait 30 more seconds and then look at the answer. Okay, let's move to the answer. So the answer is 15. Okay, so let's see why that is. So we are talking about warp 0 where the threads are numbered 0 to 7. So for thread 0, what happens? A of 0, which is 0. 0 mod 8 is again 0. Not of 0 is 1, right? So it comes down to this path. This is for 0. So 0 executes one square root instruction. Now let's think about 1, TID 1. So A of 1 is 1 and 1 mod 8 is 1. Not of 1 is 0. So it comes down to this path. And since no other element is 0, all of this A of I equal to I. So this A of TID becomes TID mod 8. And that is going to be a non-zero thing, and the not of a non-zero thing is going to be a 0. So all of those will come down to this branch. So there are totally 8 threads. One of these threads will go here. The other 7 of them will come to this branch. And here each thread executes 2 instructions, 2 square root instructions. So totally you will have a 7 into 2 of 14 square root instructions for TIDs 1 to 7 and a total of 1 square root instruction for the TID 0. So totally it is 1 plus 14, which comes out to be 15 square root instructions for warp 0. Now is this clear? Any doubts here? Okay, I'm assuming it's clear. Let's move forward because we have 20 minutes left. But stop me in case it wasn't. I don't mind going back and explaining again. Consider the following kernel snippet executing on a GPU architecture where the warp size is 16. Assume that the number of threads in a thread block at the time of launching the kernel is 32. So this is your kernel. Again, we get the TID. If TID mod 3 equal to 0, so this is a nested sort of kernel where we further check if TID mod 2 not equal to 0 and do a multiplication operation. If not, we do a division operation, right? This is the kernel. Match and pair the following. Thread IDs 1, 2, 4, 5, 7, performs multiplication operation, performs division operation, does no work. So your thread IDs are this 6, 12, 3, 9, 15. So again, this is a very longish question. So I'll maybe go back here and pause here for 30 seconds to a minute and then come back to the options. But yeah, remember that this is a nested case. So think of that divergence example that you studied in class where there was a 2-level branching. So warp size is 16, number of threads per block is 32. And if it's mod 3 equal to 0, you have a further check for mod 2 not equal to 0 and then you do a multiply. Otherwise, you do a division. Now I'll go back here. Hopefully that was enough time. I'll wait for 2 minutes to get your answer. So try to write thread numbers next to this. So write thread numbers here, write thread numbers here, and therefore write thread numbers next to this. Similarly, write thread numbers here and whatever is here comes here in this case. So those are your 3 conditions, right? One is here, the other is here, and a certain number of threads might neither go here nor here. They would go to the else part of this, but that does not have any operation. Is this confusing? Do you want me to straight away go ahead and explain the answer, or would you like some time to solve it? Okay, great. Let me do that then. It will save us some time. So the answer is D. But let's D, which means that 1, these perform the division operation, 2 does no work, and 3 performs multiplication operation. Let's go back now and see how we get to this, right? So warp size is 16, which means your thread IDs go from 0 to 15. Now, if thread ID mod 3 equal to 0, so which threads would come here, right? Whatever is a multiple of 3 would come here. So this 0, 3, 6, 9, 12 and 15 would come here. Then further, so these are the threads that kind of go through this, and after that you check if thread ID mod 2 not equal to 0. So this one is basically it's not a multiple of 2, right? And this is a multiple of 2, this is a multiple of 2. So all these get eliminated. So at this point you get only 3, 9 and 15, right? Those will do the multiplication operation, because beyond this there is no check. Whatever gets past this, that's the multiplication operation. Now in the else part, all the other things, whatever is not a multiple of 3 will come to the else part. So that would be, for instance, 1, 2, 4, 5, 7, 8 and 10, 11, 13, 14, right? This is how you would actually try and understand this. Now let's see the question. So the question asks, what do threads 6 and 12 do? So 6 and 12 are multiples of 3, so they come here, but they are multiples of 2, so they get eliminated in this second if condition. So if you remember, only 3, 9 and 15 do the multiplication operation. So 6 and 12 do no work, whereas 3, 9 and 15, which are multiples of 3 but not multiples of 2, perform the multiplication operation. And 1, 2, 4, 5, 7 are all from this else part, which do the division operation. So it comes to 1 goes to B, which is 2 options, but 2 goes to C, which makes it option D. Now is this clear, or is some part still confusing? I'll wait a few seconds. Okay, I hope this was clear. Let's move on. Okay, this seems to be a repeated question. I think we already went through it, so let's skip past it. Oops. So this is the next question. Consider a GPU architecture with the following constraints. Total number of threads in a thread block is 512. Maximum number of threads in the X dimension is 256, in the Y is 256, and in the Z is 8. Considering a 3-dimensional CUDA kernel, which of the following thread block configurations is feasible? So you have 4 options. Look through them and tell me. Okay, A, 256, 256, 8. One thing to remember is that we always start numbering from 0, not from 1. So think about that and think if it would still be A. Okay, let's look at what the answer is. I don't think this needs a lot of time. So the answer is this. So, okay, the other thing to keep in mind is also this limit of 512, right? So, so if you have the maximum number of threads in a thread block as 512, then 32 into 16 into 8. All of these I think will be greater than 512. So you can quickly use, let me just check that, 32 into 16 into 8. Yes, that definitely is more than 512. 32 into 16 is exactly 512. So looks like that's also a different way to use this criteria to kind of eliminate the options, and you end up with option D, which is a valid option. I think this is also straightforward. Any doubts here? Okay, if not, consider a GPU architecture where the warp size is 16 and a kernel is launched with a configuration where the total number of threads in a thread block is 32. Consider the following conditional statements in the kernel: tid x.x less than 16, mod 16, mod 32, divided by 2 greater than 0. Which of the following is correct? All conditional branches are divergent. Conditional branches 1, 2, and 3 are not divergent. Conditional branches 2 and 4 are divergent. 1 is divergent. So I'll go back here. Warp size is 16. Threads per thread block is 32. So now you're asked about all of these conditions. So I'll give you 2 minutes. Think about it. Any answers? This is sort of similar to what we already solved. I'll wait 30 more seconds and then we look at the answer. Okay, if there are no answers, let's look at the answer. So the answer is B. 1, 2 and 3 are not divergent. So let's look at if that is true. So your warp size is 16, right? So you have thread ID 0 to 15 in warp 0 and thread ID 16 to 31 in warp 1. Now if thread ID less than 16, which means all of these would fulfill that and all of these would not fulfill it. But within each of these warps, there is no divergence. So this is not divergent. Then we'll come to mod 16, right? So all of these one second. 1, 2 and 3 are not divergent. Is that true? What happens to thread ID 0, right? 0 mod 16 is 0, and all of the others are, yeah, I'm not sure about this answer. I don't think this is the right option, because 0 to 15, in this case, 0 mod 16 would be 0, and that would evaluate to false, whereas all of the others would evaluate to true. So this would be divergent, this also would be divergent. Let's see what other options there are. So I'm right now going with this is wrong. All conditional branches 1 to 4 are divergent is also false, because we saw that 1 is not divergent. Conditional branches 2 and 4 are divergent. 2 is definitely divergent. X by 2 greater than 0. Yeah, that also, if you take 0, 0 greater than 0 is false, and that would also be divergent. So conditional branches 2 and 4 are divergent, seems to be the right answer. 1 is not divergent, because 0 to 15, all of them evaluate to true. So I think this needs to be changed. I will update it before I post it onto Google Slides. But the answer is C. Conditional branches 2 and 4 are divergent. Is this clear? Okay, so we'll move to the last question for today. Consider a kernel processing a 2D matrix of dimensions 2048 cross 2048, where each thread is assigned to perform an operation on a single element of the matrix. The kernel is launched with A32-2 and 64B2. What are the values of A and B? Select from the options below. I think we solved a very similar one last class, so you can take a minute and come up with the answer. Okay, in the interest of time, let's actually go look at the answer. So it is option A. So how do you get that? So how many elements or how many threads do you have totally? Because every element is handled by a different thread. So total number of elements or total number of threads is 2048 into 2048. Now you are given two elements of this grid and block dimensions, which is 32 into 2 and 64 into 2, right? And the product of these two, as we already discussed, gives you the total number of threads, which should be equal to the right hand side. So you will get something like A cross B equal to some value of x, right? And what you then do is to multiply each of these things and see if they come out to be the x value that you have. For instance, here 32 into 2 becomes 64, and this becomes 64 into 64 into 2. So let me just work that out. 2048 into 2048 divided by 64, again divided by 64 divided by 2. which comes to 512. And so you need to see which of these options come out to be a product of 512, right? So 32 into 16 gives you 512, whereas 64 into 6 gives you 384, and 64 into 16 gives you 1024. So this is the only option that fits the bill. Therefore, your answer is A. Is this clear? Great. So with this, we come to the end of today's problem solving. I think there are two questions that were asked last week, but since we are almost at the 2 hour mark, I will do them at the beginning of the next lecture. So today we have 1 more minute. I'll wait on the call to see if you have any more questions or doubts. If you do, please post them on chat. If not, thanks a lot for joining the live session today, and hope it was helpful and useful and you learned something from it. And look forward to seeing you next week. Thank you. I'll be dropping off in about 30 seconds. So if you have any questions, this is the last chance to ask them. Okay, it looks like there are no further questions. So thanks again for joining, and see you all next week.